The last tool that we want to talk about is Cachegrind. And it's another one in the Valgrind package, and it is really much more performance-oriented than the other tools that we've talked about today. I mean, yes, something like memcheck or Valgrind looks for errors in your program that are likely to lead to slowdowns, memory leaks are bad, or prevent you from introducing an error in parallelizing your program. But Cachegrind is really about doing a simulation of how your program will interact with cache and giving you information about how you will do on branch prediction. As discussed earlier, cache misses and branch mispredicts have a very significant impact on performance. Remember that a miss from the fastest cache is maybe a 10-cycle penalty, but going to memory might be 200 or 300. A mispredicted branch has a penalty of something like 10 to 30 cycles. So, anything you could do that would reduce those costs will eventually be a significant benefit for your program, especially for the longer that it runs. In the course repository, there's a C program that from a previous course, ECE 254, that's used for some of the data in the notes. We can also, of course, look at some actual programs when we compile them. But Cachegrind reports data about first-level instruction cache, so the I1 it's referred to in the output, which is your level 1 instruction cache, and then your first-level data cache, D1, level 1 data cache, and then your last-level cache, LL is how it is denoted, and for most of the processors that we're going to talk about, that's level 3. For most of the operations, we probably actually want optimizations turned on. We'll see a big difference actually between a program where we do the optimizations on versus optimizations off. In any case, just to give you an idea about how to read this, this is again looking at the C program, so it's not entirely representative, but we can see that there were 310,670 instruction refs, of which 1,700 were misses, and then last level instruction misses 1,292, and our respective miss rates of 0.54% and 0.41%. For data references, we had 114,078, of which 77,789 were reads and the rest were writes. We had this many data misses, and it's pretty good. It is pretty good at telling you exactly all the information that you need to know, and our last level refs, and then finally a little summary about branches and branch mispredicts, and there were 7,202 mispredictions, of which 6,699 were conditional branches, and our mispredict rate was about 10.8%. Okay. This is what happens if I recompile that program with optimizations enabled, and we can see actually that it does make a difference. Comparing them side by side is a little hard in the slide format, but we can see there were fewer data references, there were fewer last level cache references, there were fewer branches, and fewer mispredicts, even though the rate didn't change very much. Still, that's actually kind of beneficial. Right? There were fewer branches, and we got fewer wrong, and also fewer right, but the total number of cycles that would be lost to mispredictions makes sense. Our instruction miss rates went down marginally. Things are okay. So the total cycles lost is decreased, and that's really the value that counts. If it's not as clear-cut, you can easily do a calculation. If you just look at last level cache misses and say on the one side it's 4,544 and on the other side it's 4,487, and just assume it takes 200 cycles because the branch miss penalty is also, let's say, 200 cycles. Whatever it is you want to do for your calculation. It should probably say 20 cycles for branch miss penalty. But if we're just looking at the last level misses, it's from 908,800 to 897,400, and that's a decrease of 11,400 cycles. It's not a huge amount, but hey, it's free money, as the saying goes. You can also look at the Cachegrind's more detailed output. It produces a file like cachegrind.out.pid, and again, it's not superhuman readable, but we can ask the Cachegrind annotate tool to look it over for us. Producer-consumer problem, the one that we don't do the optimization on. And we'll see up at the top, actually, it said something about, so it's found a level 3 cache. We'll use that for the last level simulation. And we'll let this run to the end. And for the record, if you missed it, this is the debug configuration, so it's before any optimizations. And we'll see if actually any of the optimizations are going to make a significant difference in this program. As with your typical Valgrind stuff, this will take a little bit before it is done. And magic of editing, here we are. So there were 1,238,393,256 instruction references. We had a miss rate, and well, we had all of our summary data as we expect. We have a lot of data references, and we also have a significant number of branch mispredictions, which is also kind of interesting. We have in total a 12.1% miss rate. Okay, so let's build the release version, which will hopefully only take a minute. Boy, this keeps happening to me. Okay, problem solved, hopefully. Actually, we don't want to run on the debug version, do we? We want to run on the release version. And see if that produces a better result. So, magic of editing, I'll see you when the results are in. Well, at a glance, certainly it was faster. You didn't see it because I edited it out for the most part, but it was faster in that regard. But you'll notice also that our branch mispredict rate, for example, went down a lot. We had also a significant improvement in our miss rates, which is interesting. You'll notice, in fact, that the instruction miss rate is basically 0 because there were a lot of instructions, but we do the same instructions over and over again. So once we have them, it's easy to just keep reusing them, and we don't have to do anything new with them. We don't have to get new instructions. So let's look at Cachegrind annotate on the cachegrind.out.19672 file. Right, this also has to get piped to less to get more useful. It is unfortunately a little bit hard to read. I'll zoom out a little bit. That will make it really hard to read if you're looking at it on a screen that isn't that big. But ultimately, what I can show you here is that we have on the leftmost column the instruction references. You can see exactly what instructions are going where, and so in this program, a lot of time is spent on add permits and acquire, trying to get the semaphore, mutex lock, mutex unlock, that sort of thing. If it happens to be our code that's running as opposed to a library code, it's a lot. Again, it's hard to see in the release version, so let's actually look at the other one, because the release version has some of the names mangled a bit. But we could actually see in our code where is our time going, and you can sometimes even get actual lines of code that are shown to you where it says, aha, like here's this for loop, that's what's happening. In this kind of program, that doesn't happen because, well, we're looking at things at a function level inside of Rust, but that's okay. It still shows us something that is kind of interesting to us, and hopefully when you're looking at your program, you can understand, where are cycles going. This being the unoptimized version, we can see that a lot of stuff is actually happening with the slice, iterating over the slice in a mutable way. Again, a little bit surprising. You would expect in the program actually that it would be spending more time waiting on semaphores and stuff like that. But you can see what a big difference that the optimizations are making here, because with optimizations we spend most of our time waiting on semaphores and stuff like that. When we don't have optimizations turned on, it appears we end up spending a lot more time just messing around with slices and iterating over them and everything, which suggests that there is significant improvement to be made if you see something like that, which is again neat and maybe a little bit unexpected, but hey, that's how you learn, and you will find something new, find something interesting. A good use case for something like this would be figuring out if a particular change was effective or not. Did it improve the runtime of your program? Possibly. But you can also find out why that is by looking into, well, did we decrease cache misses, or did we just decrease time that was spent waiting for things, or did we improve our instruction locality? It gives you an explanation that says this wasn't just random chance, which could be very valuable in justifying your change if somebody is curious as to why it worked. As we have just seen, Cachegrind is very verbose, and it can be difficult to come up with useful changes based on what you see, and this is assuming that your eyes don't just glaze right over when you see the numbers. You're like, yeah, the words have meaning, and meaning does a thing. Probably the things that have your biggest performance impact are looking at last level cache misses. Those appear as DLMR or DLMW. You could also look at the BCM and BIM, those are branch mispredictions, to see if you can provide a hint, give a better hint, or organize your code in such a way so that a branch is maybe no longer necessary, or is at least easier for the CPU hardware to predict. But as I've said, the use cases for those are sometimes difficult to actually carry out. It's hard to look at that output and say, aha, on this line I'm going to make this change. But in an after-the-fact version, you can figure out something about, like, why did this hint work? Well, it decreased the mispredict rate by this much, thus allowing you to estimate what impact a particular change had, if any. The other thing, of course, is that if you want to know more about Cachegrind, well, it does have a manual, and the manual is worth reading. Not that anybody reads manuals. It is more likely that what you will do is you'll give it a shot, and when you get stuck, you Google the problem, and you click on Stack Overflow, and Stack Overflow, hopefully the first answer is useful to you, and you can just pick it up and run with it, and carry on from there. But it will really depend. The use case that you're looking for may be very niche, in which case, you're just going to have to look at that manual. I know nobody wants to, but you might have to.